Hello everyone. Welcome to our session. I'm Hongcai from Huawei. I'm one of the maintainers of Karmada project. I'm glad to be here with my partners.
Hello, my name is Michas Szacillo. I work on the streaming platform team at Bloomberg, and we're a user of Karmada.
Hi, I'm Tessa Pham. I'm a senior software engineer at Bloomberg. I'm working on the AI training and notebooks platform.
Hi, I'm Zongqing from Trip.com, an online travel agency based in China. Thank you.
Okay, here is our agenda today. First, I will give a brief introduction to Karmada project, and then my partner will dive into our new features over last year and some use cases. So at the last, I will cover the community status. Okay, before we get started, I want to know how many of you have heard of Karmada before? Please could you repeat? Oh, awesome! Thank you. So basically, Karmada is a project that help you managing multiple Kubernetes cluster, and it can help you to schedule your workloads among different clusters. And the amazing thing is that if you are going to migrate your application to Karmada, you usually don't need to change anything to your application. So that's because Karmada speaks the Kubernetes API. And another amazing thing is Karmada can support every kind of workloads, no matter the Kubernetes deployment jobs and any workloads like Spark, Flink, and PyTorch. So also your customized resources. Okay, I will hand over to my partner for the next part.
Great, thank you. I'll use the laptop, that's okay. Hello, everyone. So Karmada is a rapidly evolving project. We release quarterly, and over the last year, we've created a lot of new features that have been created with the community. We can't talk about all of them today, but there are a few that we're going to be talking about in more detail. So first, with stateful application cluster failover, Karmada already provided a way for users to monitor cluster health and trigger cluster failovers in response to cluster outages. However, at that moment, cluster failover is still a very disruptive process, and it was something that was primarily used for stateless applications. Recently, we added support for stateful applications, and you can actually conserve state when transitioning applications from one cluster to the next. So starting from version 1.15, the cluster failover feature has added support for this, and it allows you to define the types of state that you may want to conserve for applications during failover. So let's take, for instance, one cluster decides to crash, and Karmada will reschedule your applications to another cluster. In this case, let's assume that they're all stateful. Well, you can use the state preservation feature, which just extends the existing API defined in the propagation policy, and it's comprised of two fields. The first is a JSON path, which is just an expression that targets a specific piece of state that you want to conserve, and then the alias label name. So this will just be whatever you want to call your label, and then it'll be up to you to consume that state once the application is failed over to the next cluster. Now, let's say that you have cluster failover enabled in your infrastructure. How do you actually ensure that the fallback cluster has sufficient capacity? So if all clusters are saturated and one cluster goes down, even if you have cluster failover enabled, those workloads won't have space to get failed over and rescheduled to the next cluster, and it's going to make failover useless. And as a result, you really need to capacity plan smartly. And this is where federated quota enforcement comes in. So this was added as part of Karmada v1.14, and it allows us to set resource limits directly on the Karmada control plane level. So you can apply your resources directly to your namespace. You have a federated resource quota synced to that namespace. And then before the Karmada scheduler actually decides to schedule your application, it'll double check that the resource that it's scheduling isn't going to go over your limits that you currently have set in your federated resource quota. So just to give an example, let's assume a user's managing 2 jobs, each using 10 CPU, and you have a federated resource quota that has 20 CPU as the limit. So both those applications can be scheduled no problem. One gets scheduled on cluster member 1, and then one gets scheduled on member 2, both consuming 10 CPU. In the future, let's say the cluster goes down, well then we have sufficient capacity on the second cluster for your other application to get rehomed. If we didn't have this type of federated resource quota, a user could just blindly be applying applications until they saturate all the member clusters, and at that point, failover won't work. So moving on to other features, some of our users deploy applications that are very sensitive to downtime, think on the order of seconds. And in that case, you may want to schedule multiple applications to different data centers for high availability. This was the main motivation for workload anti-affinity, which lets users define logical groups that they can associate separate workloads with. So in this example, we use a group by label key called pipeline ID. We schedule 2 separate workloads, and we group them based on the actual value, so in this case, indexing job. And that way, Karmada can logically group both of those separate workloads and decide to schedule them to separate clusters. The inverse is also supported. Let's say you want to co-locate a group of applications on a single cluster. You can set the same exact type of label key. In this case, we have some sort of training jobs that we'd like to collate on one member cluster. In that case, Karmada will automatically detect that they're related and should be scheduled to the same place. And then additionally, we've added support for multiple component workload scheduling. I'm assuming most of us here aren't scheduling just Kubernetes native resources. A lot of the time we're using something like a CRD, and then the CRD operator takes care of translating that CRD into Kubernetes native resources. So when it comes to Karmada Scheduler, it needs to understand the amount of replicas that CRD is going to have and the replica requirement for each resource. Now, with CRDs that have multiple components, this becomes a problem because since Karmada is assuming that the replica requirement is going to be the same, you can actually lead to inaccurate resource quota usage. So you can estimate incorrectly. So let's say we have a Flink deployment here that has 2 components, one being a job manager and one being a task manager. They can have vastly different resource requirements. And as a result, we can either underestimate or overestimate the total resource usage, which can lead to inaccurate scheduling. So now that that's supported, if you apply a CRD that Karmada can interpret, once it gets applied, the Karmada controller will extract that information into the resource binding, determine the component requirements, and then be able to actually schedule that requirement based on the total usage and find a member cluster that is suitable. And next, I'm going to hand off to Tessa, who's going to talk a little bit about priority-based scheduling and her use case.
All right, thank you, Michas. So last but not least, we have rolled out a new feature in the past year as well. When you have multiple workloads all competing to get scheduled across federated clusters, you need a way to tell Karmada that one workload is more important than another. And that is what priority-based scheduling does. It ensures that critical workloads will get scheduled first. The workflow is pretty simple. You first will create a standard Kubernetes priority class with a numeric priority value. And then in Karmada's propagation policy, you will add a schedule priority subfield that will reference that priority class by name. Now, this gets handed off to Karmada Scheduler, which will queue the resource bindings based on priority from high to low. And if they are ties, they will be broken by first in, first out order. If there's no priority class specified, the priority will be defaulted to 0, and that resource will sit behind any resources that were prioritized explicitly. So in this example on the right, we have a deployment called Critical Nginx in the default namespace. And we're telling Karmada that this resource takes high priority and to propagate it to member 1 and member 2 clusters. This diagram will demonstrate the queuing behavior more concretely. So let's say in the priority queue right now, we have a couple resources, and a user comes in and submits a new resource that resolves to priority of 500. Where will that go? With priority scheduling, it will sit behind the job or the resource with priority 1,000, and it will be scheduled before the one with priority 20. And this will guarantee that critical workloads are not starved behind a flood of low priority submissions. Next, we'll move on to talking about use cases of Karmada in the real world. Starting with Bloomberg, we have been an active adopter of Karmada, and we have integrated it in multiple projects in the past. In the past year, we've extended it to 2 more projects. The first one is model cache. We came up with a CRD so that we can cache a model on every node to save startup time. I'm not going to go into the implementation, but if you're curious, you can check out the link down below where my colleagues have explained it. But we basically built out a model cache API that is a thin layer that sits above Karmada. So how it works is when we receive a request, it will route it to the Karmada API server, which will then propagate the resource to all nodes and clusters. And with model cache, we want to cache it on every node and cluster. On the left-hand side, you will see this is the response we get back from the model cache API, which has the info of the model. But the most important thing is the status. It will indicate what nodes the model failed to cache on and the status of the ready nodes, whether it is being downloaded, there was an error, or it's downloading. And we get all this information from Karmada API server. Why do we pick Karmada for model cache? Simply because the multi-cluster federation is exactly what we look for to cache models at scale. Karmada can natively fan out resources to all clusters, which is what we need for model cache. So we don't have to write any custom script to do so per cluster. You'll also have flexible control over where to place a model cache if you choose to by using propagation policy, which can target the caches by cluster profile, GPU availability, region, or any other labels that you want to match. And finally, on the roadmap, a future item that we can do is we can also feed the inference traffic metrics into the scheduling decisions so that Karmada can prioritize caching the model that has the highest demands. And some more features that we also get out of the box with Karmada is one, global status. We only need to query Karmada API server for all the statuses of resources on member clusters. And how do we do that? We specify the logic to aggregate status in the resource binding. So if you have multiple clusters where a model is cached on, how do we decide that that model is successfully cached? You can specify, you can customize this logic and then ask Karmada, what is the status? Karmada can also auto-detect and reconcile when there is a failure in any cluster, and it will reschedule the model cache to other healthy clusters. And finally, if there is a change to the propagation policy, you only need to make that change in the policy, and Karmada will reschedule the model caches accordingly without you having to touch the member clusters at all. At Bloomberg, we also offer Jupyter Notebooks that is packaged in a job. We offer that to our internal users. And the problem is, how do we schedule a Jupyter Notebook on any cluster that has available resources? So here you see we have a notebook that requires V100 GPUs. How do we schedule that? Again, we come to Karmada, and Karmada can smartly pick a cluster that has V100 GPUs and also available number of GPUs to schedule this Jupyter Notebook job to. Again, Karmada can intelligently place this notebook given the resource requirements. We don't have to write custom script. And again, we can flexibly place this notebook where we want it based on GPU requirements or based on region, if you want to schedule the Jupyter Notebook on the same cluster with any other resources that it needs. And again, features out of the box with Karmada is global status. So with Jupyter Notebook, you don't really need to know what cluster it gets scheduled to. You just ask Karmada, what is the status? And it'll give you that. Aggregated status, you can customize what it means for a notebook to be live and running. Karmada can reschedule the notebook to a healthy cluster if a cluster fails. However, you'll lose the job that is already in the notebook, but that is not Karmada's fault. And finally, when it comes to resource contention, you can use priority scheduling to schedule any notebooks that needs to be urgently used. We don't have that. We don't have that need at Bloomberg right now, but that is definitely something we can do in the future. Now I will hand off to Zongqing to talk about how Trip.com is using Karmada.
Thank you, Pham. Hello, everyone. I'd like to share how we use Karmada in our multi-cluster architecture to improve the delivery efficiency and system resilience. We use Karmada to quickly distribute cluster add-ons and build a resilience-first, high availability architecture for stronger fault isolation, and enable smooth large-scale cross-cluster application migration. In the past, when we brought out a new cluster, multiple teams have to manually deploy networking, monitoring, logging, and many other Kubernetes add-ons and other supporting components. These were also ordering dependencies between these components. So initialization often took several days. Now with Karmada, we can distribute these foundational components in a unified way. We can only need to make one configuration change in the Karmada propagation policy, and all the components can be automatically rolled out and made ready. Today, this capacity already covers more than 40 clusters. It has reduced the time needed to bring a new cluster online from several days to less than 4 hours. This has significantly improved our delivery efficiency and helped us respond much faster to the business growth. The second improvement is resilience at the architecture level. Because a large portion of Trip.com traffic is transaction critical, and because traffic demands a high elastic, we need not only HPA-based scaling, but also a very high level of availability. So we design an architecture like this. We spread stateless applications across 2 or more member clusters, and each cluster runs its own independent HPA component. When a member cluster serving live traffic fails, traffic is automatically shifted to other clusters based on the health checks. While HPA is triggered to scale out and complete the self-healing process. Even if the federation control plan is temporarily unavailable, it only affects application updates and rebalancing. It does not affect HPA-based scaling for running services. In fact, our SLA allows the federation layer to be unavailable for up to 1 hour. This architecture gives us core services stronger, high availability, and disaster recovery capabilities. The third improvement is a smooth cross-cluster migration. As our business has grown rapidly in recent years, some of our clusters once exceed 4,500 nodes. So we often need to split the clusters and migrate applications to the new clusters. In the past, we did not really have an administrator-side migration capabilities. Application migration had to be triggered by service owner through new releases, which was both time-consuming and very costly. Now we only need to adjust the weight in the Karmada propagation policy, and the workload will automatically scale out gradually in the target cluster, will scale in the source cluster, enable smooth migration. We have also, with this mechanism, we have already completed large-scale migration across more than 10 clusters, involving a total of 300,000 pods in a stable way. Here are some numbers. Automated baseline rollout reduce add-on deployment time from several days to less than 4 hours. Today, this capability covers more than 40 clusters, and one of the Karmada control plane manages around 25 clusters. Our smooth cross-cluster migration capabilities has already migrated more than 300,000 pods, and our distributed HP-based resilience architecture ensures that fault can be isolated to single cluster. Today, these capabilities are already running in production across multiple regions. Looking ahead, we will continue to improve cross-cluster scheduling and explore more possibilities for large-scale multi-cluster system. Thank you. Next to the Hongcai.
Okay, thank you, Zongqing. Okay, I will talk something about the Karmada community. Karmada was open sourced at 2021 and become a sandbox project that year, and then moved the level to incubating in 2023. And now we are in progress of the graduation. We have a lot of contributors and also public adopters. Also some cloud providers are also using Karmada to build a cloud service. We always listen to our end users, and we also build a dedicated team for scalability. By the way, the scalability team is led by Zongqing, and we also have another team for the dashboard. Okay, here is our public adopters. All of these are using Karmada in production, and we have set up a Karmada adopter group team, and to help them, we always welcome all of the users to join the group, so you can connect to other end users and share your experience and looking for support or something. Okay, that's our roadmap this year, and for the past 2 years, we are almost focusing on supporting AI workloads, and we have finished the priority-based scheduling last year, and the next we are going to cover the preparation part, and also we want to have a better multi-class queue, also for AI jobs, and also a lot of guys are using Karmada between their self-built data center and the cloud. So we also need another feature for for people to select the classes between self data center and the class and then the public cloud. And also process cluster resource aware scheduling is a small part. And also I want to always looking forward more feedback for the product, so we can add more to the project. Okay, I think that's all. So I think we still have some time. So if you have any questions, okay. Thank you, guys.
I have a question. Thank you for the talk. And does the failover work? You said the quotes and stuff like that. Does it work with the cluster autoscalers? For example, that you don't need to over-provision the failover cluster, so this workloads would be rescheduled and cluster would autoscale as well.
If I'm understanding the question correctly, you're saying how does federated resource quota work if there's a cluster that's auto-scaling?
Yeah. So if the target cluster, is set up to autoscale, yeah, it would work as well.
Yeah, I think that should work as well. I mean, ultimately, federated resource quota is just meant to be on the Karmada control plane level. So
it doesn't check available resources actually in the cluster at the moment.
Checking available resources is happening during the scheduling cycle. So like the first portion of each scheduling cycle, you take a look at each cluster that matches your cluster affinities, and then you're taking a look at the amount of available capacity on each cluster. So if your resource that you're trying to schedule to that cluster is going to go over the available capacity on that cluster, it won't get, like that cluster will get scheduled out or filtered out of like the scheduling candidates.
That's the question. So if it doesn't have at the moment, but it would be auto-scaled if you would provision it there.
Oh, I get you now. Yeah, I don't know if that's currently supported then, because the only thing that we see is the snapshot of that cluster at this given moment.
Okay, so you need to over-provision kind of, yeah.
Yeah.
Okay, clear.
Hi, thanks for presentation. I was curious about federated resource quota, it's called, right? Is it per namespace?
Yeah, per namespace.
Okay, so Karmada awares about each cluster quotas, right? Is it CPU memory and or every resource, like config max and so on? All the specs, right?
Yeah.
Cool. And another part of the question is about the Karmada performance. Did you face any issues with it when you are scaling with the amount of clusters? As Karmada has some kind of control plane components and so on, and what kind of issues you faced, if any? Thanks.
I don't know. Hongcai, do you have opinions on that?
Yeah, for the performance thing, we have run a performance test at 2022, and Karmada can support about 100 clusters, and so we are going to have another round of the performance, as we have made a lot of improvements for the past year. So I think we are going to working on that this year.
Thanks.